Okay, for comparing functions, this should actually be after lesson 5.3, so ignore that that says 6.3. We need to make sure that you understand how to compare functions when they're represented in two different ways. So, for example, on this worksheet, on this first problem, we have a function that's, oh, whoops. A function that's written, sorry about that, in an equation form, and then you have a function represented over here in a table. So we're basically comparing to make sure you understand what the slopes of each one would be when these two functions are represented in two different ways. So if you can see past my little scribble here, the f of x equals 5x minus 2. Okay, this one's going to be fairly easy because the slope is the rate of change. So if this is multiplied by x and then there's a minus 2 after, then whatever's multiplied by x is per each time we move, per the domain. So this is going to be our slope. So it's 5. Whatever is multiplied by x is the slope. So 5 or 5 per every 1 if you want to put it in a fraction form. But the slope, the rate of change is 5. In this one, remember that the rate of change or the slope is always whatever your y's are doing over whatever your x's are doing. So it's always y's over x. So if we find out first what our y's are doing, it looks like it's going up 2 more, up 2 more, up 2 more. So the y's are changing by 2, positive 2. And then let's check the x's. These are going up 1. From 0 to 1 to 2 to 3 to 4. Those are going up 1. So it's 2 over 1 or just 2. So if we compare the slopes, the slope of f is 5. The slope of g, because it's g of x in this one and it was f of x in this one, is 5 versus 2. So the slope of f of x is steeper. You could also say larger than the slope of g of x. Okay, next we're going to look at two more comparisons. So you've got your comparison in a table like we had before, and now you also have the comparison with a graph. So let's see if you would know how to compare functions from a table to what it's doing in a graph. So f of x is the one in the table, and then g of x is the one that's on the graph. So the y-intercept is what we're looking at this time. So basically, it's going to be easier to look at the one on the graph because we can spot it right away. Your y-axis, wherever your line hits the y-axis, boop, right there, is your y-intercept, because that's what it means. It's intercepting the y-axis, and it intercepts it down here at -1. So it intercepts on g of x at -1. Really quickly, let's decide what that ordered pair would be. I marked it right here. It would be 0, -1. So if you think about it, any y-intercept, no matter where it hits the y-axis, is going to be 0 something. So when we look at it in a table, you're looking for when x is 0, what y is. So 0, -3 would be here, which means that's where it would hit the y-axis. So its y-intercept is -3. So anytime x is 0, your y is your y-intercept. So comparing these two now, you can say something like the y-intercept, I'm going to abbreviate it to y-int, of f of x is lower. When I think of lower, I think of on the graph it would be lower. Or you can put less than the y-intercept of g of x. So, and the reason it's lower or less is because -3 is less than -1. -3 would be lower than -1 on the y-axis. Okay, now we've got a word problem about two friends, Connor and Pillar, are rock climbing in a rock climbing club. They're climbing down a canyon wall. Connor starts at the cliff 200 feet above the canyon floor and climbs down at an average speed of 10 feet per is where you're going to put your x, minute. So right away, I want to go ahead and write this equation down because I'm thinking about it. He started at 200 feet and he's going down 10 feet per minute. So I'm subtracting. I started at a height of 200. That was my initial amount, my initial height, and I'm going down 10 feet per per minute. So that's why I'm subtracting 10. I'm going lower from the starting amount of 200. Pillar, his climb down the canyon wall is in this table. So this is Pillar. So at 0 minutes, he was way up the climbing up the wall at 242 feet. And after only 1 minute, he's down this far. After 2 minutes, he's down this far, and so on. So we are going to look at these two different people and compare them based on just words and based on the table. So Connor is the one that I kind of wrote out the equation up here. Connor's initial value was 200 because he started at 200 feet above. And his rate of change is negative 10 because he's going down 10 feet per minute. So I guess I could go ahead and put 200 feet and then negative 10 feet per minute because a rate of change is a rate, feet per minute. Okay, and then Pillar's height, he originally at 0 minutes was way up at 242 feet. And he's climbing down. His rate of change is also negative because he's going down. And if you look at what you're subtracting, it looks like his rate is steady at, what is that, 8? Looks like 8 feet per minute. So he's negative 8 feet per minute. So then again, let's compare the two. Oh, it says both interpret the rates of change and the initial values. So whereas up here we just did the rate of change and here we did the initial values, now we're doing both. We're comparing both. So let's look at just the initial values. Looks like Connor is at 200 and Pillar is at 242. So you might say something like Pillar's initial value was more, or was, we can just say more, that's fine. But I would say, though, that Connor's rate of change is more. So, but Connor's rate of change was more. So actually, we would need to continue this out because even though Pillar started up higher, he's climbing down at a slower rate. And so Connor, even though he was already lower, so if Connor was already lower and he's climbing down faster, he's definitely going to finish faster. So Pillar's initial value was more. Connor's value is faster. I might put faster because rates of change have to do a lot of times in this situation with speed. Okay, let's look at the back. So one last thing, this table is really important. It's got a lot of really good information on it. Y equals mx plus b. This is slope-intercept form. Slope-intercept form. So anytime you hear the terms, put this in slope-intercept form, that means we want y by itself. You guys have finished, you've done the rearranging to get y by itself a lot. And then you have the slope, which is m, squished up against the x. It's being multiplied. That's the rate of change or the slope. And then plus b. B is whatever the initial amount is or the y-intercept. So m is always going to be a number that represents the slope. B is going to, or the rate of change. B is always going to be a number that represents where they started from. So sometimes it's a negative number, but the standard form of slope-intercept form is putting it with a plus because you can always have it be a negative amount. So again, slope is the value whatever m is. B is the value of whatever the y-intercept is. And we're going to work more on this if you haven't already, but to find the actual slope, you would put a y coordinate subtracted from another y coordinate if you happen to have two coordinate numbers. Like if you had 1, 3 and 2, 4, you would take the y value and subtract it from the other y value, and you divide it by an x value subtracted from another x value. So that's if you have two ordered pairs. And then it kind of walks you through how to get it into slope-intercept form. And then you also could do it from a graph. You could choose 2 points on the actual line and find the rise over the run, the change in vertical, which is going up, which is rising, and then the change in horizontal, which is running, which is going left to right. So rise over run is also going to give you that slope value, that rate of change. And then find the point where the line crosses the y-axis. That's what we did on the other side of this paper. That's where we find the y-intercept. Okay, so let's look now at the slopes and y-intercepts of this equation and table. So again, the slope is the number that's in front of x. If it's in slope-intercept form, which it is, the y, the f of x is also a y. It's by itself, so it's already in slope-intercept form. So this is going to be our slope, and this is going to be our y-intercept. So the slope of this one is -1/2. And the y-intercept of it is -2. In this, the rate of change or the slope, remember it's always your y over your x. So it's whatever y is doing over whatever x is doing. So let's check. The y's are changing by going down 3. That to that is -3, -3, -3, -3, so -3 over the x's are going up 2 each time, so -3/2. And remember, if it's a weird fraction that won't simplify, just leave it. So we're going to leave it -3/2. And remember, the y-intercept is when x is 0, it's whatever y is. So if 0, 1 is a point, that would end up being on the y-axis. 1 is your y-intercept. So now that we've found them, we're comparing the graphs. If you have an initial value of -2 versus 1, then this initial value is going to be much lower. And then if your slope, both of the slopes are negative. So when we compare, we can say both slopes are negative. But going down every 1/2 is going to be less steep than if you go down 3/2. So the g of x, this one is going to be steeper because it is going down and over more. So both slopes are negative, but the g of x is going to be a steeper negative. Excuse me. And then on the y-intercepts, what are we saying? Comparing, okay, the y-intercept, I'll abbreviate it again, the y-intercept of f of x, this is this one, begins lower. So it hits on the y-axis at a lower spot. So it's lower than +1, which is the g of x. Okay. And then the very last section, now it's just going to go ahead and say, okay, now we've got an equation and we've got a graph. Tell me what the slopes are. Tell me what the y-intercepts are, and then compare again. So the slope of f of x, remember, it's the number that is m. It's the one that's next to the x. So 6 is the slope. And over here, the slope, let's see how, we know it's going down, so it's decreasing, so it's going to be a negative for sure. Excuse me. So let's see how steep it goes down. I would put a dot wherever you can find that a corner hits, like maybe right there. It hits in the corner right there. It hits in the corner there. So it is the rate of change. It's going down 3 per every over 1. So the horizontal change is 1, and the vertical changes, it drops down 3. And remember, rates of change, slopes are going to be constant, or else it'd be zigzaggy. So since it's a straight line, it's going to go down the same amount and over the same amount every time. And that is what the slope is, or the rate. So this one is going down 3 over 1, down 3 over 1, down 3 over 1, down 3 over 1. That is the vertical change over the horizontal change. The y's over the x's, just like we did here in a table, the y's over the x's, the rate of going up and down and then going over. And so this one is -3 over 1, which we'll just call -3 because anything over 1 is simplified to say just the number above. Okay, and then the y-intercepts, this one, the y-intercept would normally be plus b, but since it's a minus b, a minus 1, it's going to be -1. So the y-intercept here is -1. And then let's see where the y-intercept is on our graph. It is right at the origin, which means it hits the y-axis at 0. Okay, so a real quick comparison will show us that this slope is going to be going uphill, whereas this slope is going downhill. One is positive and one is negative. So f of x's slope is positive, while the g of x's slope is negative. So one is going up and one is going down. And then I would say, based on the y-intercept, f of x's y-intercept is lower. It will hit at -1 than the g of x's, because the g of x's hits at the origin itself. So this one will hit the y-axis at 1 lower.